and in this case, the jet engine is kind of completely removed, and you have some sort of energy storage, most probably batteries, and these batteries are feeding a number of electric motors that are driving electric propellers. The last figure below the all electric figure, which is titled partial turbo electric, that's mainly what is considered for large commercial planes, because relying on energy storage would be a very heavy and expensive option. So the idea of partial turbo electric is that part of the power is kind of channeled or funneled from the turbo fan or the jet engine through an electric generator or generators, and then this electric generator is feeding a number of electric motors that are driving a number of propellers. So again, there are kind of different system architecture that have been considered over the last few years. I'm sorry, I'm having difficulty even progressing the slides. I don't know why. Just give me 1 second, please. Yes. Okay, let me run. Can you guys see the full screen now? Can you tell me which slide you can see? I mean, I'm having great difficulties for some reason, you know. Okay, but then the slides are not moving for whatever reason. Okay, yeah. So the next slide. Let me see if it's. Yeah, okay. I don't know how it progressed, but there has been a big shift in the aerospace industry. So companies like Siemens, which used to play no role or in the aerospace sector at all, kind of started developing electric motors and drives for the aerospace sector, and they developed one of the earlier motors and drives that have fairly high specific power or kilowatt per kilogram, and that was unheard of at the time. I think that was the time frame was like 2015, and that section in Siemens eventually got bought by Rolls-Royce. Can you guys still see my slides?
Yes, sir. This slide is visible. It is on the same line. Now it's fine. Now it's exactly correct.
Okay, now it works. Okay, good. So you guys now see the slide with the number of planes, small planes?
Yes.
Okay, great. Thank you. Thank you. I think I fixed it eventually. Yeah. So this slide kind of shows a number of examples of different concepts for small planes that are used or considered as for air taxi, for package deliveries, and you can see that there are many familiar names here. I mean, there is Airbus, Aurora is like part of Boeing. Lilium is a company in Germany. So there is a large number of startups, maybe a couple hundred at least, startup companies that are working on different concepts for electric and hybrid planes. This slide kind of shows a timeline of some of the test planes that have been kind of developed and tested over the years. So again, many of them come from Airbus, from NASA, from others, but the ultimate goal of this space is to kind of electrify or hybridize the single-aisle commercial planes where the engine power is around 20 megawatt. And as you can see here, this is still kind of the timeline of when this is going to be accomplished. It kind of says 20xx. So I mean, initially, people were talking about 2030 as a target, but probably things are going to take longer than that, especially when it comes to the certification process. This also shows another timeline for some of what is referred to the vertical takeoff and landing or eVTOL. So also there are a number of concepts for eVTOL that are being pursued right now. Again, for some of them are by Uber and others. So again, it's a very active space. But the main idea here, in order for the electrification or hybridization part to be effective in reducing the fuel consumption, etc., is that the electrical components that are going to get added, whether motors or drives or energy storage, have to be fairly light. Meaning that the goal is, for motors specifically, since I'm going to focus on it, is that it needs to be like 2 to 3 times lighter than the state of the art. So I'm going to kind of focus on a specific project that we have been working on over the past 4 years now, and this is part of something called Ascend program that's funded by the Department of Energy in the US. And this is again targeting a hybrid system, as you see here on the left, where we're going to have the engine and then a number of motors driving propellers, as we discussed before. The figure in the middle kind of show the mission profile that's going to be required out of the electric motors. So during takeoff and climb, 250 kilowatt of power is going to be needed for a couple of minutes. And then after that, during cruise, the power required drops to about 83 kilowatt. So the performance targets for this project is that we need to accomplish a machine or electric motor specific power greater than 20 kilowatt per kilogram. That's a very high number. And a machine efficiency based on that mission profile greater than 93%. And the overall system, basically including the motor, the electric drive, and the thermal management system, needs to be greater than 12 kilowatt per kilogram. And if we go with a direct drive system where the motor is connected directly to the propellers, the propeller speed is 5,000 RPM, and the DC bus voltage needs to be at least 1 kV. The reason why for electric and hybrid propulsion higher voltage is needed, because especially in larger planes, the typical system voltage in aerospace is either 270 volts or plus or minus 270 volts. So if we stick to that relatively low voltage and we are asking for hundreds of kilowatts of propulsion power, then the amount and the weight of the electric cables needed is going to be very significant. So part of the reason why with all these activities the system level voltage has been pushed to few kilovolts is really the weight of the cable. But kind of as a feed forward for what I'm going to talk about next, the higher DC bus voltage, especially at altitude or reduced pressure when the plane is flying, it increases the risk of partial discharge and corona effect significantly. So in electric machines and drives, the insulation systems are much more significant and much more thicker. So the big challenge in that case is how to extract the losses / heat from the electrical machines and drives with such high system voltage. I'm just going to briefly tell you who are our partners. Marquette University is leading the overall project and the motor and power converter development. Florida State University is working on the development of the insulation system. As we mentioned, because of the higher voltage at altitude, we need a new insulation system to avoid partial discharge and corona effects. The National Renewable Energy Lab, which is one of the national labs in the US, is working on the development of the thermal management system, or TMS. And we have two industrial partners, Raytheon, which is one of the big companies in the commercial as well as on the defense side of things. They are helping with the system integration and also verification testing of the drivetrain that's being developed. Ampere is a startup company in the Los Angeles area, and they are working on a small hybrid plane for urban mobility applications. So this slide is busy, but I'm kind of, I don't know, and I'm not really sure how many of you have background in electrical machines and power electronics, but I'm gonna kind of walk you briefly through what are the key things that are done differently in this project to achieve very high specific power that's required for the application. So what you are looking at here, hopefully you can see my cursor, but what you are looking at here in the first figure to the right is additively manufactured coils that are hollow. Basically, they are hollow, and you have access to the internal space inside the conductor from both ends of the conductor. And these are made out of aluminum alloy. The reason is that aluminum alloys are much more advanced than copper when it comes to additive manufacturing and kind of maintaining tight dimensions and tolerances. Also, aluminum is lighter, and also, without going into the very fine details, but this conductor is, at the end of the day, is a solid conductor. So, and the frequency of the machine in this case is over 1 kilohertz. So the AC losses in these conductors are more significant than the DC losses. So the lower electrical conductivity of aluminum helps in that case. The kind of golden components that you see inserted inside the conductor, these are copper heat pipes. We kind of chose, in this case, heat pipes because they don't have, they are kind of a passive device. They don't require significant pumping requirements. But that being said, nothing prevents us from replacing heat pipes with like pumping air or fluid like oil through the conductor. But what this shape of the coils enables us is that since we have complete access into the conductor area, that basically we can extract heat from inside the conductor without having to be penalized by how much insulation is wrapped around the conductors, which represents a big thermal resistance. The other figure to the left at the top again, we also have a segmented stator structure. So what you are looking at is kind of a part of the stator
core with 2 teeth, and then you have like a pair of the additively manufactured coils inserted in that part. So this kind of shows the repeated or the building block of the motor, basically, of the stator part. The other thing is that if you look at these windings, even though they look, or these coils, they look very different, but in the end they are what is referred to as fractional soft concentrated windings or tooth windings, where the length of the end windings is very short, and that has a big impact on reducing the overall length and size of the machine and minimizing the losses in the end region, among other benefits. The rotor is not shown here, but I'm going to show it to you later. The rotor is made out of something called the Halbach array, so it also eliminates the need for back iron on the rotor side, which makes the design even lighter. In terms of the drive or the power electronics, as you can see in the two figures underneath, that instead of having one big inverter, three-phase inverter feeding the whole machine, we have modular power electronics where what you are looking at is like one power module, and each power module is effectively a single-phase H-bridge that feeds the pair of coils that are shown at the top. So basically, that a pair of coils fed by one power module is kind of the building block of the overall system. And because of the modular nature of the power electronics, the 1 kilovolt DC bus voltage is kind of divided among 6 modules per phase. So the voltage per module, the DC bus voltage per module, is less than 170 volts, and that enables us to use GaN devices, gallium nitride devices, at that low level of voltage, which also allows us to have higher switching frequency and good quality current waveforms injected into the motor with fairly low THD. Also, this modular structure allows us to have very tight integration between the machine and the power electronics. And also this modularity, depending on how we do the control, allow us to have some level of fault tolerance in the system, which is very important in safety critical applications like aerospace. So in case we lose a section or more of the system, we can potentially continue producing power out of the other section without interruption. This is kind of showing, I mean, it's complicated here, but this is kind of showing the overall system, CAD drawing. Once you kind of integrate the motor with the power electronics, you see that this becomes a very compact system, and we are kind of what our predictions tells us now, that we are gonna be around 11 kilowatt per kilogram in terms of the specific power of the overall system, and we should be able to meet the efficiency, the system efficiency requirement. I'm just gonna walk you through the various steps that go into designing something like this. So obviously, the first thing we focus on when we are designing an electric motor is that we do extensive electromagnetic optimization. So this is kind of showing, we are using something called differential evolution, which is a genetic algorithm kind of optimization. So you see that we consider different slot pole combinations for the motor design, did extensive optimization. This table is a busy table, but it kind of compares the different optimized designs, and we consider direct drive designs and other designs that were geared, meaning that we include the gearbox to increase the speed to reduce the size of the motor. But what we down selected out of all of this is a 36 slot 30 pole machine with direct drive at 5,000 RPM. So, but a lot of analysis and a lot of optimization went into that decision at the beginning here. This system, since it's very unusual, it needed a lot of de-risking from the very beginning. So from the very beginning, we had to start building hardware and characterize it maybe from day one. So when it came to the coils, when we started that project 4 years ago, the concept of additively manufacturing coils that go into electrical machines was not very common at all. Additive manufacturing was well known and used to build parts for various things, but not for windings or coils of electrical machines. So we had to work with multiple vendors and test a large number of coils and see the quality of the additive manufacturing, the surface roughness, etc. Also, these vendors don't provide you with any electrical properties of the coil, so we have to do our own testing to validate the electrical conductivity and its thermal coefficient, as well as how the coils behave under AC and DC excitation. So the coils were tested initially up to 250 amps RMS and a frequency of 800 hertz. And also we needed to quantify how much are the losses in the coils, and also another key factor, what is the impact of the different interfaces between the interface materials between the coils and the heat pipes. And also we looked, I should have mentioned that for those of you who are not familiar with heat pipes are like have an evaporator section which kind of absorbs heat from inside the coils, and then they have a condenser section that gets kind of connected to what's referred to as a condenser chamber or heat exchanger, where heat is rejected. And that condenser chamber could be cooled by either air or liquid. So we also looked into both options and did a lot of characterization and testing. In terms of the heat pipes themselves, they also needed a lot of independent characterization. So we tested a large number of heat pipes, different sizes, length, and different vendors. We considered both round as well as flattened heat pipes to determine what is the heat carrying capability of the heat pipes. Also, we looked into the impact of the condenser temperature, and I will show you later. We evaluated something called single and dual condenser. The single condenser is that if the heat pipes are only protruding from one side of the machine, and the dual condenser configuration if the heat pipes are protruding from both sides of the machine. And as we will see later, this has a big impact on the thermal performance of the system. The insulation, we had to do a lot of also various testing of the insulation system, because it's a critical part, as we said, especially with the increased risk of partial discharge and corona. The second figure that you are looking at here, this kind of shows a complete section of the stator with the heat pipes integrated. We refer to it, this is kind of one-to-one scale. It's basically it's the full scale section of the motor, and we refer to it as motorette. So we built a number of these motorettes, and we did extensive testing of these motorettes with air and with fluid, and also we did partial discharge and vibration testing that I will share with you a little bit later. And also the drive, I'm going to talk about it in details, but also the drive, we went through various generations of the drive or the power module design, and that went into different type of testing, double pulse, DC and AC testing, in addition to also thermal testing. Because the power electronics also, as we'll see a little bit later, are cooled, using heat pipes. I'm just going to show you samples of the detailed analysis that's needed for something like this. So what you are looking at here to the left, this is kind of one of the designs of the condenser chamber. This is additively manufactured and also made out of like some plastics. And the heat pipes are eventually connected to the condenser chamber. So we had to do a CFD analysis to determine the heat transfer coefficients, and then feed that into a thermal model to determine what will be the maximum coil temperature. So as you can see, based on the analysis, the maximum coil temperature was in the range of like 140 degrees C, while the core, the stator core itself was around 105 degrees C. This is also, since I'm kind of running out of time a little bit, these are the round heat pipes that are used. What you are looking at here is kind of the GAN devices that are cooled by round heat pipes. So also we did CFD and thermal testing of the heat pipes for the power electronics side, and the analysis showed that the maximum device temperature is going to be around 115 degrees C, which is acceptable as long as we don't, our threshold was a junction temperature of around 125 degrees C. This is showing one motorette or one section of the motor. The green parts are the condenser chambers, and we did vibration testing on a shaker setup at Raytheon to make sure that we don't have any big issues with vibration, especially that we have these heat pipes protruding out of the motor and connected to them these green parts that are the condenser chambers. This is just kind of a nice dynamic picture showing the different modes that were experienced during that vibration testing. But the bottom line, the conclusion here is that really nothing showed up as a source of concern, and the frequency behavior of the test object, the motorette with the condenser chambers, was the same before and after the vibration testing. This is the rotor, the section of the rotor. So that part that looks like a spoke, this is part of a titanium hub. And as I mentioned, we have a Halbach array. So each magnet pole is divided circumferentially into 4 segments. Each has different direction of magnetization, and this is what allows us to eliminate the back iron in the rotor. And the magnets are, there is a carbon fiber retaining sleeve that holds the magnets in place. Extensive mechanical analysis and stress analysis was done at 20% over speed to ensure the integrity of the rotor. And also, as I will show you later, we actually built a full-scale rotor, and that went through an actual spin test to confirm these results. Again, we also went through a lot of analysis looking at the rotor dynamics and the various modes, and confirming that there are no critical modes within the speed range that we plan on operating the system at, and that was confirmed. There is a lot of details here. Some of you, if you have some mechanical background, you might be familiar with something called Campbell diagram. Here, this is showing that we also had to do a lot of insulation testing to determine the partial discharge inception voltage, or the PDIV, at what level of voltage would we observe partial discharge. So there were measurements, coil to coil, coil to core or ground, and kind of this shows you the details of where the probes and the measurement points were. This shows kind of a summary of the PDIV results under AC excitation and under PWM excitation. And this is for coil to ground and coil to coil and turn to turn. And for each of those, this was done at three pressure levels, basically. The largest PDIV occurs at sea level, and the 50 millibar is kind of equivalent of an altitude of about 30,000 feet, which is typical for large planes. So you can see that the partial discharge inception voltage decreases with pressure or altitude as expected. So these results actually kind of guided us to modify our insulation system and increase the thickness of the insulation in certain parts of the system to increase the PDIV to an acceptable level, especially when it comes to the coil to ground and the turn to turn. Just to give you an idea how compact this system is, this is a mock-up, a 3D printed mock-up of the system. So the gray parts are kind of the stator of the motor, the blue parts represent the power modules. So, and these kind of brown sticks represent the heat pipes. But this is what's kind of interesting about this is that what you see sitting that you can put on a table is a full-scale or one-to-one representation of how big this system is, and taking into consideration that this is a 250 kilowatt, to be that compact and to be that small, that just shows you the kind of challenges to reach that level of compactness, basically. This is kind of showing the motorette with dual condenser. So you can see here in this case that the dual condenser is, as I mentioned, the heat pipes are protruding from both sides of the motorette. If it was only pushed from one side and protruding from the other side, that would be single condenser. So here with this, in this case, you can see these green things are kind of open. So this is for air cooling. And this kind of shows the details of the test setup, but this is kind of shows the kind of temperatures that we were getting out of the motorette, and you can see that we were at a coil temperature that's again comparable to the 140 degrees C that came out of the analysis that I showed before, the CFD and thermal analysis. And also we did testing at using liquid cooling, as I mentioned, but I'm not showing the details now. This picture shows, or this figure shows, the first rotor that we built. So what you are looking at here is kind of, what you see here is like a spoke wheel. This is the titanium hub, and the black thing is the carbon fiber wrap, and underneath it are the magnets, the Halbach array that I kind of showed you in previous slides. So this first rotor went through a spin test, and it kind of passed to confirm the integrity of this motor. This is kind of just shows you the actual magnets. These are the 4 segments per pole, and these arrows are not like great, but each black arrow kind of indicates the magnetization direction of each of these segments. And also the magnets are segmented axially to minimize the eddy current losses in them as well. Again, I'm kind of have a lot of material, but moving forward, this is kind of showing the power module. So we have like 3 boards per module. One of them is the power module that has, the power board that has the devices, the gate drivers and stuff like that. And the second board is the one that has capacitors, and the third board is a communication board. And if you look to the figure at the very left, this kind of shows how the system looks like when the 18 power modules are in place and fully integrated with the motor. And kind of, again, the figure in the middle shows what we talked about before. This is kind of the repeated or building block of the system of one power module feeding a pair of coils. So here, this is a busy slide, but it is just showing you that we went through all kinds of issues from one generation to another of the boards, whether it's the type of devices we are using, the mounting of the devices, other things. So we had to fix many things as we progressed toward the final solution for the power module. This is just showing a sample of the test results. When we were testing the power module, the 166 volts this is the rated voltage, and the 268 amps RMS, this is the rated current of the system. So this is showing a sample of the test results, and that also the temperatures were below 100 degrees C. This is kind of showing again a video of us testing the power module with the motorette. The other important thing is that if you look at the quality of the current waveforms that are injected into the motor, the THD, our goal was always to be, especially with the weighted THD, to be below 5%. So you can see that we were able to accomplish that. And in terms of like the absolute THD, we, depending on the operating point, we are somewhere between, let's call it 4 and 6%. So, which is acceptable, because when we looked at the impact of this THD, or we injected these current waveforms into the machine, they didn't introduce significant losses that would affect the machine efficiency, basically. I'm trying to wrap up this topic, but this is kind of showing you briefly the thermal test and the heat pipes. What you are looking at here to the left, these round golden components, these are the heat pipes coming from the power electronic side. So basically, there are heat pipes that cool the stator of the motor and heat pipes that cool the GAN devices, and both get connected into a shared condenser chamber at the end of the day. This is kind of showing the temperature as a function of current, and you can see that we get that green curve. Kind of the blue curve is when we use a classical large heat sink, and the red one is when we are using a fan, and then the green one is when we use heat pipe with liquid cooling, which is the ultimate solution. So you can see that we get the best performance or the lowest temperatures of the GAN devices or switches when we use the heat pipes and the liquid cooling. I mean, we have a lot of references. I know I'm moving very fast here, so I apologize, but we have a lot of papers published on the topic. So if you are interested, just reach out to me and I can provide you with more information. In the remaining few minutes, I'm just very quickly gonna walk you through another important topic. All of you are aware of the issues related to rare earth materials and the need to eliminate rare earth materials because of geopolitical reasons. So we have been also working with the Department of Energy on developing low-cost drivetrain for EVs and HEVs. And we have partners, a company called Niron Magnetics, that are developing rare earth-free magnets called iron nitride magnets. We have Virginia Tech working with us on the inverter development, NREL working with us on the thermal management, and General Motors or GM is our industrial partner that will help with the system integration and also the verification testing. I'm just going to skip through a lot of the slides, but what is the issue is with rare earth material. This kind of showing the forecast for where neodymium iron boron magnets, which include rare earth material, neodymium, dysprosium, terbium, etc., that you can see that there has been an increase over the years in terms of what are the applications that use rare earth material. And the issue is that back in the 2011-2012 time frame, there has been, if you look at that blue curve for dysprosium is one of the materials that are referred to as heavy rare earth material. The price went up by more than a factor of 5 or 6. So since then, there has been global effort to see how to reduce the dependence on rare earth materials, especially for EVs and HEVs. As you can see, for EVs and HEVs, the industry for the past couple of decades have shifted towards what is referred to as interior PM machines. So this is kind of showing samples of the rotors of different motors for some of the Toyota Prius, Ford, Honda, others. Today, because of that, and usually like each car has 1 to 2 motor/generator, and each machine uses around 1 to 2 kilograms of rare earth magnets. So this is kind of, if you do the math of how many million cars are sold every year, so that tells you the volume of magnets that are needed. And also, if you look at something like wind generators, roughly, this is not very accurate, but for wind turbines, we use about 1 metric ton of magnets per for each 1 megawatt of power. And today, as you know, for onshore wind, the wind turbines can go to up to 5-6 megawatts, and for offshore wind, you can go up to 15 or so megawatts. This is the largest wind turbine today. So some companies today, like BMW and Volkswagen and others, moved away from permanent magnet machines and kind of, I don't want to say reverted back, but they moved to wound field synchronous machines where the magnets are replaced by electromagnets in the rotor side. Again, I'm going to take like five minutes to wrap this up, but these are kind of the cost and power density targets and the voltage targets we are looking at. What we are working on is the Chevy Bolt system. The Chevy Bolt is a pure electric vehicle that was produced by General Motors. As I mentioned, our partner Nylon Magnetics are working on developing something called iron nitride magnets. This is kind of the baseline design that we are comparing ourselves to. This is an a 2-layer V-shaped IPM machine, and this is designed for a DC bus voltage of 800 volts and the maximum speed of 16,000 RPM. Our approach to how to reduce rare earth material is that we looked into combining different types of magnets. So as you see, based on the color codes, this kind of the red color is kind of, it's kind of one type of magnet, and the other color that's kind of, I don't know whether it's gray or green, but this is another type of magnet. So we looked at different magnets combination, kind of, these are the pH curves of the various magnets, combining neodymium magnets with iron nitride, dysprosium-free magnets with iron nitride, dysprosium-free magnets with ferrites, and neodymium magnets with ferrites, and then ferrites with iron nitride and pure iron nitride. The combination C5 and C6 would lead to designs that are completely rare earth free, and the first 4 should lead to a reduction of rare earth content, but not complete elimination. Whatever the approach that you take to reduce or eliminate rare earth material, the 2 things that you worry about are, 1, whether you can meet the same or have the same torque producing capability as the baseline design, and the second one is when you are using non-rare earth magnets, usually these are weaker magnets with lower coercivity, so they potentially tend to demagnetize. So we did a lot of work. This kind of shows various designs with 2 layers of magnets and 3 layers of magnets for the various combinations. But here is the bottom line, this table kind of shows a sample where you can see, it's a busy table, but if you focus on that first row that says neodymium reduction percentage, you can see that some designs can achieve up to 60% reduction in rare earth content. And since these are high-speed machines, so obviously we had to make sure that, and we are using more magnets because we are using like weaker magnets, so we have to make sure that the mechanical stresses are acceptable at the top speed. This is showing demagnetization. We check demagnetization at the minimum temperature of -20 C and the maximum temperature of 150 C, and this is kind of shows that for all the designs there is no significant level of permanent demagnetization. And this is kind of shows the torque speed curves for the various designs, and the conclusion is that most of them are able to meet the torque speed curve of the baseline design without significant demagnetization. So where we are now, we are in the process of testing a motor that we built. So we kind of, this slide shows the laminations for one of the designs that was shown before that is going to combine dysprosium-free magnets plus ferrites, and this rotor got retrofitted inside the Chevy bolt system, and we are in the process of testing it to see how it performs compared to the baseline design. I'm very sorry that I was very fast. I know that I had a lot of material, but thank you for your patience, and we'll be happy if there is time to kind of try to answer some of your questions. So I see a question in the chat, in the chat room. So I think someone is asking what would be the kind of liquid cooling that would be suitable for an outer rotor. I think whether inner rotor or outer rotor, what it boils down to is that you cannot have a conductive fluid inside the machine. So it depends on where that fluid, if it is spray cooling or contained within a cooling jacket. If the coolant is going to be sprayed or is going to enter the machine somehow, then that needs to be some sort of oil or transmission fluid. If it is contained in a cooling jacket and it's not going to leak, then you can potentially consider something like water ethylene glycol, which is kind of conductive in that case, electrically conductive. Thank you. Yeah, thank you very much. Yes. I hope so. We still have a lot of work to do, but I appreciate the kind comments. Thank you. Sure. Yes. So sorry, what you want to know? Why did we do additive manufacturing? So yeah. So maybe I can just give me 1 second, you know. So I will give my screen. Sorry. Oh yeah, I mean, if you look at this figure, you know, these gray parts, these are kind of the additively manufactured coil, right? I mean, so these are kind of it's 3D printing, so you print them in that shape layer by layer, right? And then how they get inserted, because we have a segmented stator structure. So as you can see here, you are going to have 2 teeth, and then you can just slide the pair of coils to kind of get inserted into into the stator teeth. So what you are looking at here, I don't know, hopefully you can see my cursor, but this is kind of showing the 2 coils inserted into 2 stator teeth and back iron, basically. Why we do that? Because as I mentioned, that shape you cannot accomplish with regular wire, right? I mean, to have access, to have a hollow conductor like this where you can extract heat from inside the conductor, that's very difficult to accomplish with regular wire, obviously. Even though there are some hollow conductors that you can bend them to make a coil out of them, these are commercially available, but the problem is if the size of the machine is small, and depending on the bend radius, these hollow conductors, the conventional hollow conductors might collapse while you are winding them. That's why they fill them typically with sand or something similar. And also, if you have a hollow winding and you are kind of making turns out of it, usually to pump fluid inside it, that requires quite a bit of, leads to quite a bit of pressure drop, and the pumping requirement is very significant. That's why when you do it additively, you get that unique shape of the winding or the coil, where you have kind of a hollow space inside the conductor where you can slide or insert the heat pipe or pump air or fluid without any complications, basically. I don't know if I answered your question, but feel free to reach out, and I can, by email or something, and I will be happy to provide more information. Oh, hi. Yeah, hi. How are you? Hi, good to see you. I'm good, thank you. Thank you very much. Hi, everyone. Thank you very much for inviting me. It's a great pleasure here. And hi. Yeah, very nice meeting all of you. And if anyone have any questions, please encourage them. They can contact me by email or something, and I will be happy to provide more information. No, you are very welcome, and best of luck with the conference, and I hope the rest of the conference goes well. Yeah. Great. Congratulations on another successful event, and hopefully we will meet again soon. You know. Okay. Yeah, thank you again. Thank you very much for having me. I mean, the level of activities that you guys have is very impressive, and it's very encouraging to see all these conferences. And it has been a pleasure and honor to present to you. And hopefully, I'm looking forward to hopefully attending one of the conferences or this conference in person, maybe the next year or after it. So again, thank you very much. Thank you very much.
You are most welcome to be in Silcon next year.
Thank you very much. You guys enjoy the rest of the conference. Okay, take care. Bye-bye.
Bye.
সুমন, রে সুমন, লাইট বেড়ে ডাইরেক্ট সাদা তুলে দিয়েছে।
Our next expert speaker is Subrata Chakraborty, scientist from ISRO who began his career with Thermals Limited
সুমন,
in the process heat division in the late 90s. Since 2001, he has been with Indian Space Research Organization and who is responsible for the design, development, qualification and operation of electromagnetically actuated valves like solenoid valves, bistable valves, proportional valves and mixture ratio control valves used in ISRO's launch vehicle and spacecraft missions. Presently, he heads the solenoid valve design division in Liquid Propulsion System Center of ISRO in His notable contributions include delivery of 58 valves in the illustrious Chandrayaan-3 mission. His team has also contributed 24 valves for the important Aditya L1 mission. His team has so far delivered close to 200 solenoid valves which are currently operational in several on-orbit spacecrafts of India and another 1,500 more which have already served their purpose. He and his team now devote much of their time in developing valves with features like manual orbit rights for human interfacing, mechanical latching and added coils for enhanced redundancy for the upcoming human-rated Gangayaan mission of ISRO. He was the recipient of ISRO Young Scientist Merit Award in 2008 and published close to 20 papers in national and international journals. So I request Sri Subrata Chakraborty for an enlightful discussion.
Beginning to this conference where the leading lights, I would say, have all converged here from this zone, and it gives us a good opportunity to interact with the students, the future of the industry, and I always look forward to participation in such events because in a way it is like a homecoming for me, and I get opportunities to interact with all of you. So the past 2 or 3 years in ISRO was quite eventful, and first of all I'd like to thank the organizers for this opportunity. And getting back to the point, past year or 2 was quite eventful in ISRO, and we have been working on this area of electromagnetic actuators, mainly valves, which are like on-off devices, proportional devices, and which find extensive application in space, on orbit, both in spacecraft as well as in launch vehicles. So this Chandrayaan thing happened after a failure, most of you are aware, in 2019. We nearly made it, but there were some software glitches which were overcome, and the fear of failure and the probability of success was increased considerably, as our chairman always says. And now in 23rd of August, National Space Day 2023, we finally made it, and it was a concentrated effort of several teams, subsystem designers, system designers and all. And of late again, that was a very eventful area, that era of 5-6 months where several lunar missions were happening back to back. So we'll be discussing on that as well. I hope to give you a flavor of what it is all about, what is this happening all around us. Then several geopolitical developments have also took place, like our previous speaker was also talking about the rare earth materials. And we have the samarium cobalt, neodymium iron boron permanent magnets, which are made from samarium, from rare earth materials. And fortunately or unfortunately, China holds 80% of the world's reserves on rare earths. So for geopolitical and strategic reasons, people want to have it, alternate sources, so which Professor Refaie has pointed out that his team is already on the job. So that is where we are heading to actually. Then we also had the Boeing Starliner has come into the news because they had a space mission where they ferried the astronauts to the International Space Station, and our Sunita Williams was one of the co-passengers. A technical glitch happened and now she is stuck up there at least in February, mid of 2025 is what they said. She has managed to lose some 15 kgs of weight because of lesser calorie intake. So everything is happening at the same time, and there what it becomes important is docking. So we'll cover a little bit of that also, what is docking and why is it so important, and where do we stand as ISRO? What is ISRO doing about it? At the very onset, I would like to say that the difference between ISRO or any other similar organizations, research-oriented organizations like BARC or DRDO lies in the diversity of operations. With due regards to BARC, it's doing pretty well, but DRDO mainly devotes its time on developing missiles and ammunition for the Indian Air Force. Now, what happens to these missiles? Like we have of late you must have heard about the Pinaka missile. BrahMos is known to you. It's a joint collaborative exercise, but Pinaka is in the range of 70 kilometers. Okay, there are several things to talk on this area, but the main difference I would like to highlight is it revolves around the controllability. It is all about solid propulsion. In rocket launches, you will see that there are stages separating out in a phase-wise manner. Because of the famous rocket equation, if you see the equation, you will identify or know. Because when you take off a rocket, a heavy-built launch vehicle, it takes off the thrust is important, specific impulse or mileage is not so important. As the spent stages get ejected one by one, you find that mileage or specific impulse becomes more important. So, and there is good controllability. You can restart an engine if it is liquid driven. But talking about solid missiles, you don't have that option. Once you ignite a solid missile, you ignite a BrahMos, it will go and it was to hit the target. It is having navigation, guidance, closed loop feedback control, all those things are all there. 300 kilometers is its stated range. It will do its job and that's it. Whereas in a liquid engine, you have several acrobatics, several gymnastics, several things are possible. So there you see the diversity, the flexibility, the design has to cater to all those kind of things. But typically speaking, aerospace is a one-dimensional science. Why? Because it is very high in velocity. It doesn't have any other dimensions basically. We say rocket science, but rocket science is again one-dimensional. But obviously the numbers are very high. For example, like talking about the International Space Station, you have the Falcon 9 rocket. It has a Dragon capsule. And it is fired by a Merlin engine. It has to reach 300 kilometers. It does so when the when the Crew Dragon is separated from the launcher, Falcon, it has a speed of 28,000 kilometers per hour. 28,000 kilometers per hour is its speed. And if you compare it with suppose a Rafale fighter, Dassault's fighter, that speed is around 1300 kilometers per hour, roughly the speed of sound, 1 Mach. And what about the speed of F-35, the one Israel uses against all its enemies, by which it is around 2000 kilometers per hour, F-35 fighter. It is stealth. It can't be detected on a radar. It can go, do its job, come back in 2 hours. And it can fly 2000 kilometers, mind you, without any stop, intermittent stop, refueling, nothing is required. So why I am saying all this is because the intricacy, the technology is in that level. So when at 28,000 kilometers you are putting the Falcon puts the Crew Dragon capsule, what is the most challenging thing next? It is to chase the ISS, which is roughly around 400 kilometers away from Earth. It's revolving at roughly around, say, 90 minutes orbit takes. It has to go, it has to catch it, it has to chase it, match its this thing, and then it has to dock with it. And then only you see Sunita Williams floating in. She broke into a dance. So that's because the docking was done, she could come, and people were there waiting to welcome her into the ISS. So those are the kind of numbers. But here, one more problem is there. Since the numbers are so large, margin of error is also equally important. So suppose I say 28,000 kilometers per hour, the number may be baffling. But if there is a margin of error of say 100 kilometers per hour, and if it fires for 1 second more, she's elsewhere. So they need correction. So that's why you see the way it takes off, a Falcon is taking off that SpaceX, Elon Musk's rocket. It takes off. It takes 15 minutes to reach there. But to dock, it takes 30 hours. Those people are sitting there for 1 full day. The Russian Soyuz takes 3 hours. It is because the launch window is so adjusted that they will go and they will have a perfect alignment, the angles, and all these orbit raisings are perfectly done. But the capsule is very, very congested. So that's the problem. So this is the area we are working in. This is the area we are talking. And so what does this all have to do with electromagnetic actuators? Let's find out. So I'll give you 2 examples just to fire your imagination. You must have seen, now talking about the Middle East war, there are several places where there will be air bases. America has air bases in that full area, Red Sea, Mediterranean Sea, Gulf of Persia, all that area is surrounded. Then you have that Haifa port in Israel near that American air base. What do they do in that air base? They will have a launcher. It is hardly like a ship. And then they have a fighter. They have F-35 or Rafale or whatever. It takes off to such high speeds, barely from 200 meters of runway. How does it do that? You board an aircraft, it has a 5-kilometer runway, and it has 2 kilometers after that also as a protective zone. You are not allowed to construct a double-storied house in that vicinity. So how is it possible that a Mach 1 aircraft takes off in 100 meters, just like that it zooms up? It goes, obviously it doesn't go to the speed of sound immediately enough, it takes some time maybe. It is all because of EMALs, electromagnetically automatic launchers, which is there on those ships. It is an electromagnetic, it has a huge capacitor driven, which gives a momentary power in a matter of seconds. And China is mastering that technology, they are the pioneers. So far there were steam engine launchers, steam is using steam. China has gone into that. Now most of you will be knowing, Japan is where the science began. Japan is where the science began, but the technology matured in China. So whenever we talk about scaling up, we talk about fabrication, we talk about economics of scale, application-oriented usages, China is the place to be. So this is one application. Another is the maglev trains. And interestingly, this is one area which has the maximum amount of practical applications. It is not a science done in the lab. Previous speaker has shown how much of his efforts he has actually experimentally validated and proven. And the amount of simulation that has gone is starting from genetic algorithms to optimization. It is like a lifetime's work he has shown. and I really appreciate that. So this is just to fire your imagination. Now coming to the space, I think I have already covered that it is having the harshest, fastest, largest, greatest, all those numbers, it stacks up heavily in the favor of space science, and that is why it is anything you do about space is very intriguing in nature, and you have an opportunity to be associated with it. It's really worth it. Now, motivation for reaching out to space. Now, don't look at the slides, I'll just let you know. What happens is, nowadays, the lower Earth orbit has become very, very active zone, a busy zone. And you have Jeff Bezos, you have Elon Musk, everybody, even our Sunil Mittal, Airtel, they are all into this cheap internet service providing business. So they have a constellation of satellites there. One web series, Jeff Bezos is there, and then Elon Musk, I forgot the name. Okay, so there, that area is one. Another is the orbital platform. Orbital platforms are nothing but a cheap experiment. As long as you don't have the ISS, you need something or somebody or a platform or an experimental lab there. We provide it. ISRO does it. It has done it twice before, and we'll do it once again in C60 PSLV C60 December 3rd week. So that platform is nothing but the terminal stage of a rocket, which is having a reaction control system of thrusters. A series of thrusters which does attitude control, and it will be having very small pulses will be fired just for, because there is no drag, atmospheric drag is not there. You need minimum force to maintain the attitude and orientation, and there you can have a lot of experiments which can be conducted, because there will be payloads which are invited from colleges, universities, private organizations. So for 2 months roughly, you can get the data, and you can do what happens in space, because 400 kilometers means it's zero gravity. By the way, what is gravity? I mean, what do you mean by gravityless or space? What is meant by that? Space is a vacuum atmosphere where two things are happening. One is you've experienced weightlessness, of course, G forces disappear. Two more things are happening is you have absolute vacuum, you have a pressure correction. The pressure, which is absolute in nature, has a 1 bar correction. And to simulate those environments, those things, even the effect which is felt on plants, geotropism, something which people are see, if you put a plant in front of on your window in your room, it will automatically move towards the sun, and the roots will grow towards the ground. That is called geotropism. Now there are devices called as clinostats, which will sort of cancel out these forces of gravity by two angular momentum. There will be two stepper motors which will rotate in such a direction that it will cancel out that, and it can simulate zero gravity on ground as well. Then there are anechoic chambers also which are used, and for astronaut training and all, we use acceleration devices. Suppose people who are going on top of those capsules like Crew Dragon and all, you will find that they have to withstand 50 G forces and accelerations like those things. So those testing sites are also very important. So here this is roughly the motivation, and providing an orbital platform, accelerating testing of devices, helps in sort of tissue engineering. Colloidal stability. Colloidal stability, absence of coagulation and sedimentation of colloids, paints solids, and so there are, and of course the body forces disappear and the surface forces become more important. The physics changes, and that's why people want to go out there more and more. Now, where are we in India in space? Here are a few numbers just to give you a flavor. These are arguable numbers, people may agree or disagree. So Mars mission, we were the 4th nation to conduct a successful Mars mission, but that was way back in 2013. We can't rest on our laurels. There is a history to it also, I'll come to that. Human in space, India will be the 4th nation if it can successfully send and bring back a human being to and from outer space, which is planned in this ambitious Gaganyaan mission. We'll have the first unmanned mission sometime mid of next year. Lunar mission, we were the 5th country to successfully execute a lunar mission. However, we were the first to have a soft landing nearer to the lunar south pole. But story doesn't end there. A lot of setbacks were there which has helped us reach this area. Couple of setbacks I have listed here. But the most important thing which did not result in a setback is serial number 7, Mars orbiter mission. Something interesting happened in September 2013. We'll discuss about that. Now, types of lunar missions. See, a lunar mission is, it can be a flyby, or for that matter, any interplanetary mission could be a flyby. It could be an orbiter like a Mars orbiter mission. You just go there. Flyby is just passing it by. I visit your house, I don't enter your house. I say hi and go on my way. Orbiter is I keep circulating your house, rendezvous. Impact landing is when I don't have a soft lander, a throttleable engine, it just goes and bumps there. You plant your national flag and you come off. I mean, you don't come off, you do that. Soft landing is what we demonstrated last year in August 23rd August. Sample return is the next level, which is planned in Chandrayaan 4. Then landing a human being and bringing him safely is the next one. Now, if you see, this is the complexity increases from top to bottom, but the increasing complexity for the last two is exponentially very high. So we have a lot of road to cover up. Now, the recent past, as I was discussing, what was happening in all these 3-4 years? See, I'll tell you one thing. Russia is known for lunar missions. If you see this serial number 4, Luna 25, which was a Russian lunar mission. It happened in August 2023, roughly the same time when we started. But what happened? It ended in a failure. But this was the mission which they undertook after 47 years of the last successful mission. It was maybe a time when many of you were not even born. That time the last mission had gone, but that was USSR. This is Russia. There were some critical technology elements or a generational gap which had come, and that was showing. This, in contrast, there was a Hakuto R, a Japanese mission, which had also ended in a failure. The 4 missions which I have bracketed are the things which have taken place in the more or less in the 5 months time interval. Then we have the SLIM lander, smart lander for imaging moon. First one was a Japanese private mission. Then the SLIM lander, which landed in January 2024, was a huge success. Of course, the trajectory and etc. were different. And the Russian mission was also having a different trajectory. They had a powerful rocket, the Soyuz rocket. Chinese lunar sample return mission happened in July in this year. It was an audacious mission. You get an opportunity, please look up the net. They have done a sample return from the dark side of moon where there are severe communication problems. Then we have the Artemis mission, which is a manned orbiter, which is a joint, you can call it coterie of led by NASA, of course. So very few lunar lander missions have taken place in the recent past, and almost all have ended in failure. That's what made Chandrayaan 3 stand out. And it gained international prominence because of these 3 reasons. Because the successes of SLIM and Chinese was after Chandrayaan. January 2024, July 2024. But that here the story doesn't end. So lunar missions are, why they are important? 2 reasons. One, it is a stopover or a refueling station for deep space missions like Voyager and all. Some, I don't know how many thousands of crores. It's outside the solar system actually. And then Juno was a Jupiter mission. So like that, several missions are there. Then deep Perseverance. Okay, the list is endless. So deep space, NASA is the boss. Lunar missions, Russia used to be the boss. So this is the scenario as of now. Okay, I'll show you here. So now coming to electromagnetic actuators, in line with the spirit of the conference this year. Here I am showing a 3D figure in a 2D manner. You see, you have several orbit racing earthbound maneuvers once a rocket is taking off. It is to increase its eccentricity. Eventually it goes out of the Earth's gravitational field with a high enough velocity, and it goes into a lunar capture here. A lunar capture also, it will be having an initially very high eccentricity orbit. It has to So you have this kind of a eccentricity in the initial orbit after it is going into a lunar capture. So this all happens in a three-dimensional geometry. I am just showing it for your convenience. But why am I showing this slide? Or why did I tell you all this? It is just to make you realize and come up to get a taste of the flavor. So all this is happening. You are increasing the eccentricity of the orbit intentionally because your destination is 4 lakh kilometers away. You are increasing it by firing some thrusters, which is on board the spacecraft. How do you do that? You fire a valve. Which valve? Electromagnetically actuated valve. Why such valves? Because the response is very, very less, happens in 10, 20, 25 milliseconds, the actuation happens. When you see a rocket burn or take off, what is this taking off? It is the firing of a electromagnetically actuated valve. When you say 10, 9, 8, 7, 0, T0 is that firing. So basically the RCS thrusters goes up, but the first stage is obviously the solid stage that has to give provide the thrust necessary to lift this heavy vehicle. So all valves are very important for fluid control, pressure and control, synchronization effects to make the mechanisms work in perfect unison. So there only the response comes into play. So now, what are the types of valves? We have a pneumatically operated valve, motor operated valve, electrically actuated valve. So if you see the serial number, here. So cycles of actuation, 500 to 10 lakh cycles of actuation, it will operate repeatedly with amazing repeatability in the results. The response time will not vary within close tolerance of 1 millisecond, even less, half millisecond accuracy. Here is where science meets technology. And you have to make it very, very portable, compact, because miniaturization, we can't have weight penalties. So you have an optimized design. It is having high contamination sensitivity, but the best part is that the response time is very, very low. Compared to pneumatically operated and motor operated valves, motor operated valves you typically see in servo systems, the response is around 3 to 11 seconds. It has a spool, it has to move slowly, it is motorized in movement. But these are typically ground operated. These are ground operated valves which are, they form part of the automatic launch sequence. They will be factored in the abort criteria for launch hold and release mechanism. It is called as LHRS. So MOVs typically form part of that. Pneumatically operated valves are also highly sensitive to contamination and other things. Cycles of actuation are somewhat less. MOVs have 5 to 20. So this is where we are. And other types of valves are pressure regulators, pyro devices, diaphragms, bus disc, check valves, non-return valves. Now, what are the types of solenoid valves which are there in the spacecraft as well as in the launch vehicle? They could be direct acting clapper type, direct acting plunger type, pilot operated 2-3-way type solenoid valves, pressure balance single side, bistable permanent magnet based, what our previous speaker had told, more the permanent magnets, fallback arrays and all. We have some overlap in that area. Human in loop designs, upcoming Gaganyaan. When you put a person up there, the physics changes. The strategies are different. Design margins are different. You have a different approach altogether towards design. The philosophy is different. So that is called human in loop design. Reliability is most important. Now coming to a direct acting clapper type valve, what are the features of design? You can see here, I have just shown, in the next slide I will elaborate. You can just see the design feature. Okay, it is a little crowded, this slide. It has a floating armature. This armature is floating, it doesn't slide. It doesn't have a sliding metallic contact. There is no fear of any contamination generation. It can easily last 1 million cycles of actuation and 15 years in orbit. And each time it fires, it will admit the propellant, it will eject a gas with some thrust, some force, it will do some station keeping operations. It has a hard-on soft sealing. It can give a leak tightness of 10 raised to -5 standard cc per second. You can't imagine the type of leak tightness it is having. Why? Because most of the thrusters will have a fuel and an oxidizer, and both these lines will be having a solenoid valve at its end. And where they meet at the injector, just on top of the thrust chamber. They don't have any igniter. These are hyperjolic propellants. They ignite on contact. The ppm level of the fuel and oxidizer has to be below permissible limits. When you don't want it to actuate, you can't allow leakage beyond a point. So you have to have ultra high leak tightness. Otherwise, they will just come and have an unintended combustion, which will result in a catastrophic failure or a mission failure kind of a scenario. That is the first reason. So leak tightness. Second reason is, when you go for deep space mission, you want to go to Jupiter for a 9-year mission, or maybe even more, I don't know, maybe 10 years or so. If you have a leaking system like Sunita Williams Boeing Starliner, where helium was continuously leaking and they don't have the confidence to use the same vehicle to bring her back by 400 kilometers. If that kind of a scenario arises, your mission is doomed to fail even before it starts. So leak tightness, very important. And what are these gases doing there? Those gases are meant to drive several systems. Those gases will be regulated down using a pressure regulator, and it will be used as a command pressure, like a pneumatically operated valve, or it will be like, it will operate certain systems. It will act as a pilot for comparison of chamber pressure, and used in various closed loop systems also. Fabrication of metallic seats takes care of accurate geometrical tolerances, and you have surface finish, edge radius, constancy stress, and does not overheat on continuous coil energization. On response time can withstand minor excursion in operating pressure and applied voltage. Ideal for deep space, long duration missions, and pulse mode and steady state operation. Pulse mode, what the previous speaker told, PWM, pulse width modulation mode. Now this is one example. I was talking about the orbital platform. So this is how the valve looks like. You have the valve. This is the valve. This is the solenoid coil. It has some wear gauge. It is designed with some inductance, resistance, L/R ratio for time constants, and it has some power outage, joule heating, and area also. Through this, the inlet, the gas is admitted. You have a filter at its upstream. Then it goes down, and then there is a small seat-like thing, and here you have the armature. So this armature is actually, it is like an on-off valve. This valve has a 400 micron stroke. On demand, this will be actuating. It will is a normally closed valve. It will just lift the seat and admit the fluid, and then it will eject out. And this purple color magenta is a nozzle. So when it ejects out, it gives a thrust. That thrust is used for station keeping operations. And why this is important? Why this valve is chosen? If you see this curve, this is the current signature. This shows the valve on response. It is divided into two parts. There is an electrical delay, there is a mechanical response. You see a back EMF, slight droop in current. So at a given operating voltage, the on response is around 6.5 milliseconds. Then 90%, now once this is done, you have a inlet pressure rise, because the inlet pressure is the pressure prevailing in this chamber. That rise takes around another 12 milliseconds. So combined effect is around 20 milliseconds. So here, and once that happens, the inlet pressure, this pressure comes down because it is firing. That shows this is the signature of a firing nozzle, firing thruster. In this case, it is gas. It could be a propellant. It could be a pressurant or a propellant. So that is where your solenoid valves are used. It's a typical application. Now, okay, this slide I will show you a pilot operated solenoid valve. Here what happens is, okay, this slide I will not dwell much, maybe I'll just come back a little later. Okay, now coming to a typical design application like the ones we used in Chandrayaan 3, a plunger type solenoid valve. So what happens is, for a spacecraft type of valve, we have two coils. That is called dual coil redundancy. You have the one coil of the one valve will be connected in series with another coil of the oxidizer. If suppose this is fuel, this will be oxidizer. And similarly, the other way around. So each coil is meant to give you redundancy. If there is a failure happening in any of the valves, any of the coils, the other is supposed to take care of its job. So here you have a 100% redundancy incorporated. These are usually used for Chandrayaan 3 because it has to fire and there cannot be any element of chance. Now coming back to the Mars orbiter mission, what had happened in 2013 was we had connected these coils. However, this connection here and this connection here, the polarity of this connection and this connection was reversed by inadvertently by oversight. So instead of getting a additive flux, this is operating as per Ampere's law. Instead of getting a flux which is additive in nature, it was cancelling each other. So you have lost the redundancy even before the actual application. Why did it happen? Because when we make a valve, we are a subsystem design team. We belong to a subsystem design. When it goes for a system level integration, there has to be a configuration control of the drawings. In that crucial phase, a mistake happened by means of which the polarity of this coil and this coil was interchanged. So whatever flux this series is generating, this was cancelled. Net result is 0 because the ampere turns are same for both the coils, both the chains. So our ex-chairman, he thought that before the actual functioning orbit insertion in Mars orbiter mission, sometime in 2014 September, maybe 10 years before, down the line, he thought, why not let us fire both these coils and see, ensure that they work in space, because it was after 1 year it took us to reach Mars orbit. When we fired, nothing happened. Then we realized that this must have been the case. We did some documentation surveys and all. We found that we had a goof up. But finally, these are all lessons we learned. That is why interfacing, handshaking between interdisciplinary mechanical, electrical subsystems is so important. Okay, these are some other typical applications where we insert a spacer to reduce the friction, even in plunger type valves. Otherwise, you can have some deep scratches and you can't have a robust application. You will have a limited cyclic life. And these are bistable valves where you can't afford to have a continuous coil energization. You use the permanent magnet to hold the valve in its normally closed or normally open position. And you have two electromagnets. These are the, these are the two electromagnets. One is for converting the open to close, other for close to open configuration. Then now comes the important part. What is it that human rated launch vehicle, what do you mean by that? Human in loop, there's so much of talk going around there. Actually, we have two conditions called fail safe, fail operate. These are, you can look up any reliability, maybe literature. These are oftenly used. So there are 4 coil combinations. So far we saw 2 coils, now there are 4 coils. Because this launch vehicle, this is called as the Bahubali rocket, LVM Mark III. So this was the same vehicle using which we went to Chandrayaan 3 was launched in June 14, 2023. And this is the same vehicle on which the Gaganyaan also crew mission is going to go. The first unmanned, as I said, in 6 months down the line. So what happens is, if you see, look at the 4th point, if the, okay, let us say the 3rd point. If the failure of any one coil is detected in ground prior to its intended operation, the mission can be allowed to go ahead in what is known as a fail operate condition. In fact, out of the 4 coils, 2 coils are capable of actuating the valve with minimum design margin over supply voltage. 2 coils are necessary. So first one coil fails and you determine, you find it out even in ground before it has taken off, you allow it to go ahead because 3 coils are there, it will work. And everything can't fail all the time. That is called fail operate. Then what is fail safe? Fail safe is, you have launched the vehicle, people are sitting on top of it, it's gone in orbit, but then its actual intended operation has not come. It is yet to do its job, yet to ignite, yet to actuate. Then also if 2 coils are failing, suppose you have allowed in a fail operator, you have allowed with 3 coils to go ahead. One more guy fails up there before it fires. That also is okay because that is called as the fail-safe condition. You can tolerate one more fail. After that, if one more coil fails, you can't actuate. At that time, it has to actuate. So after the actuation, if one more coil fails, after actuation, the 3rd coil also fails. That is also okay. Why? Because one is called, so there is a concept called pull-in voltage, there is a concept called as a dropout voltage. A pull-in voltage is what you need to overcome the pressure forces, the spring forces, the frictional forces and actuate the armature or the plunger. Once actuated, air gap is very less. You are probably at a very, that electromagnetic, the force versus stroke curve, if you see, you are generating a lot of force there and the pressure forces are not there. You need to overcome is the frictional force and the spring load to retract it back. So that's a dropout condition. In a dropout kind of a scenario, the dropout voltage is very, very less. Because the pressure forces are not there, only spring load you need to overcome and the air gap is less. So as you reduce the voltage when it comes to be very low enough, the spring forces overcome that electromagnetic forces, it will drop out. So it usually happens, if the pulling voltage is 21 volt, this may be around 5 volt, 6 volt like that. So in that kind of a condition, once actuated, even one more coil fails, no problem. No harm to the crew. So this is the way redundancy is provided in human-in-loop missions, where people are involved. Now another application of human-in-loop missions is there has to be, this is as far as the launch vehicle is concerned, but how is reliability taken care of in capsules, in like a Dragon capsule you have, there will be several valves for giving oxygen to the suit, to the cabin. If there is a drop in partial pressure, there are valves which have to be operated. Those are also solenoid valves. 80% of valves used in launch vehicles and spacecraft are solenoid, electromechanical actuated valves. Rest assured. So here what you do, you provide a manual override mechanism. This is a symbolic graphical figure I have shown. Manual override mechanism to override coil failure. There you don't go for 1, 2, 3, triple coil, 4 coil, quadruple, nothing like that. Protection against inadvertent actuation. So manual override mechanism, if you see, this is the manual override lever. So if you have a coil, suppose there is a coil here, this is an electromagnet, it doesn't actuate, or there is a coil failure. The crew member can simply push the lever, it's like a car gear. He has to just push it, and then the valve will be opened. So he can override the coil. That's called manual override, first point. Second point is, it has to have a protection against inadvertent actuation. In space, your hands are flying around, there is no gravity, you can't control anything. So there, you just go and touch it, it will admit gas. No, it doesn't happen that way. What you have to do is, you have to have a protection against inadvertent actuation. As the name suggests, you have to first push this lever. This lever has to push, and then there is a hole here. Then there is another pillar-like thing projecting out. Then only you can bend it. First you have to push it, hold it, push it down, then only you can actually go. That is called protection mechanism. Then there is position indication, because for people down in the control center, they should know there is a micro switch position indicator. The valve is open and this is the flow. There are pressure sensors also which will detect a rise in pressure. Then there is position indicator, mechanical latching. What happens is, this part, this moving valving element, it will come down. Then there is another solenoid here in orthogonal direction. That will simply, as it comes down, it will simply latch on it, because there is a spring load acting on this direction. It will simply latch and hold its position. If you want, you can withdraw power to the coil. It will hold it. And it is, mind you, it's not a permanent magnet-based device. There is no magnet here. Only electromagnet, two electromagnet. It will hold that position. And if you want to release the mechanical latch, you have to just pull the lever. It will simply go by spring force. That's called mechanical latching. Pressure independence. This mechanical latching should not be dependent upon the pressure, because if there is more pressure here, you will have, because these are all human interfaces. The person pulling it with all that spacesuit, gloves and other thing, he will face a difference in pressure. So that it should be pressure independent design. That is another feature. So these are all human in loop considerations for crews, not for the launch. Launch vehicle is only coils are being added with different connectors. Then failure modes, heat soak back, temperature excursions during orbiting, because when you orbit, it's like your share market, you know. So on one side it could be minus 30 degrees, the other side it could be 100 degrees. So that kind of excursion you have to take care. So these are all potential, your insulation class. your any life-limiting elements, the leakage tendencies, because when you go to lower temperature, it will start to leak more. So those things and contact stresses will vary. The strength of materials will change. Spring will have a different stiffness. So you can imagine all these variables have to be factored. Then linear coefficient of linear expansion, the sliding clearances will vary for any excursions. Then Joule heating, continuous dry heating. You are not supposed to actuate a valve for without any flowing medium or fluid, because there is no convective heat transfer. So it will simply keep on dry heating till it reaches, usually it exponentiates and then it remains in a state. But the temperature to which it rises, again, it has to be experimentally validated, or some simulation studies can be done, which is usually done. That way only the resistance. We keep a limit on the current, 2.5 amperes, we don't usually exceed. Those are some design guidelines given to us. Contamination, this type of valves are very sensitive to contamination. So it's like you can imagine like a hospital, more than, a drug manufacturing center, even more than that, 3-4 times. We have got clean room classes, 1 lakh, 10,000 class, 1 lakh class. So you are all in that clean room apparels when you enter and handle such devices. Insulation failure, okay, because if the radius of curvature is high and you appear for the coil winding, if you give a load or a force slightly more than it can withstand, the radius of curvature becomes so large, the insulation can break and peel off and create shorting, and heating and those kind of things can also happen. Interface errors, like we discussed. Okay, these are the typical development. To make a product flight worthy, what is that you have to do? It is like a huge number of activities. Actuate the valve. It is just to give you a flavor, nothing much technical in this. Intro for compatibility test would be there, disassembly observations. So mainly focuses on qualification level, environmental test, vibration, thermovac, actuations, and observation, functional checks to see that the cooling voltage and all, not much of a variation is there. That way we can clear it. Future missions, so that you are also, you know what to expect from ISRO in days to come. PSLV C60, as I said, docking experiment, space docking experiment, the first one, scheduled for December 2024, third week, pre-Christmas launch. Human in loop, Gaganyaan 2026 projected, but that first unmanned mission is sometime next year. Lunar sample return mission, Chandrayaan 4, 2028. Lunar polar exploration mission, Chandrayaan 5. Beyond 2028, it's a combined mission with JAXA, Japanese Space Agency. Then Bharati Antariksh Station, 2035 we should have the Indian Space Station. So these are some photos of the Chandrayaan 3, and the interesting thing which I want to share with you is that third figure, if you see, this had come out in the papers also, you can see the depth, how with depth in the lunar surface the temperature changes. So at a depth of say minus 80 or something like that, it is minus 10 degree. However, on the surface of the moon, when it was landed, and 20 mm above, the temperature excursion shows a huge gradient, 50 to 60 degree temperature. This is measured by the CHASTE probe. I don't remember the full form for this now. Then this is where we are located all over India, mostly south concentrated. And these are the different launch vehicles in our family. And one satellite which is getting assembled in a clean room. It's a very old photo. Thanks to IEEE SILCON and IIT for the opportunity and the patient here. Thank you.
Is anyone having any query?
Nice presentation. Many things are good. What is the difficulty? Challenges and issues you are facing. Can you summarize 2 or 3 challenges and issues you are facing?
Yes. Yes. Challenges. I can give an example of the Chandrayaan 2 to Chandrayaan 3, the issues which were faced and how it was overcome. Maybe that is one example I can give, though it is not on a regular basis, but that was one interesting area. One is, sir, when we went for the Chandrayaan-2 soft landing mission in 2019 September, during the time of touchdown, there was a terminal velocity which was specified as 2 meters per second in the vertical direction. In the horizontal direction, I think it was 0.5. But while landing, there was a phase which was called as a camera coasting phase. So that camera coasting phase, there was error which was getting, positional errors were getting accumulated with no corrective actions implemented because the software did not have provision for that. There was no real-time corrective actions. It was like a, you can say it is like a closed loop, yeah, so by that time, this time what we did was, last time what happened was when it was coming down to the, and at that phase one more thing was happening was all the instruments like altimeters and all were getting calibrated also for their initial positioning and all those things, so that the height, real-time heights and all would be measured. And that phase, the air, because it is coming from a straight horizontal to an extreme vertical landing, 90-degree orientational change, this was the critical phase when this changeover was happening. And having no provision for error correction in that was very much detrimental. And it had gone into a complete tumble, and the error accumulation was so large. And there was one, our software after the phase, when it was again the error correction phase it came, it had only a provision for correcting the error up to 10 degrees per second. 10 degree per second was the error correction rate implemented, which was inadequate for correcting the full orientational error. And then when there was a firing which took place, instead of landing in this direction, it had completely reversed and nosedived into the lunar surface. So those challenges were overcome this time because there was full real-time data acquisition and corrective actions. The grid was made much larger. We had two new instruments, laser Doppler velocimeter, LDV, and a altimeter. And we used the grid which was generated by the orbiter into Chandrayaan-2, so we knew exactly where to land. And this time we could see the hovering and other things were also happening. So that was a good thing. It increased the probability of success, basically. Yeah, on a daily basis, we have a lot of issues which we face. Our biggest problem is we have issues related to valve not actuating, and valve is actuating after suppose you have an inactive storage for these valves for 6 months or so because of a launch hold or delay. You will generally find that there will be stiction between the metallic surfaces, and we have to overcome that. We have to keep on intermittently actuating them, otherwise there will be a cooling voltage excursion. So those kind of problems are there, contamination issues are there, and yeah, mainly compatibility issues with propellants, swell, duration of those things, exposure. So roughly that sums it up.
Thank you, sir, for
Thank you.
the discussion.
Thank you, all of you, for your precious hearing and your active participation and contribution to the conference. Now we'll have a short tea break. It will be my request to return within 7 minutes inside the hall. Then we'll start the program. We'll be waiting to hear from a very experienced and renowned person, Professor Ganapati Pandey sir, after the tea break. And then we'll be ending for these sessions before the lunch. Thank you. I hope you'll maintain the time. It's my request. Thank you.
Come on. Thank you.